Welcome again to everybody to this Phi-talk. This is one of a series we are organizing. We also had the past Phi-talks. You can check them on our page. I posted it in the chat. So you can find them and also check for future one. We are already planning two for February, two for March and April, so on and so forth. So enjoy them. And if you have any question, please raise your hand or chat in the chat. So thank you again. And I would say, let's start. So Nicolas, go ahead.
Oh, thanks a lot, Cristiano.
Yeah, 1 second, Nicolas, can you just refresh the presentation? I just did a quick update. If it's fine for you.
I think this is the online version, so it should be updated. No worries.
Okay,
I hope,
sure.
I hope so. Okay, right. Today we'll be talking about EVE, which is the ESA initiative on LLM with the idea to open source a neuroscience LLM for researchers, policymakers, and the public. So we are doing this initiative together with a consortium led by PySchool in Italy, with Imperative Space in the UK, with the collaboration as well of Mistral AI based in France, Paris, and also with the support of Wiley, the publisher. So I'm Nicolas JP. Together, I will be talking with Yassine from Mistral and Alex later on from PySchool. So this seminar will be about, okay, why do we need an Earth observation or Earth science, let's say, a digital assistant? Then Yassine actually will deep dive a bit more onto what they've been doing at Mistral, what the different model that they have in their pipeline, and why actually for the EVE we started from a Mistral 24B median parameter, and we'll try to explain why we started with this this baseline. And then actually Alex will deep dive into all the development that we did as part of this project. So now we started with a corpus documentation that we extracted from internet publication and so on. How we fine-tune this base model from Mistral to get it, let's say, adapted to what we want on Earth observation and Earth science. And then we'll present as well the overall architecture, the whole system that serve, of course, the LLM, but also with different elements. Then we'll mention the evaluation, and at the end, I'll do an online demonstration of the tool. So with that in mind, okay, why do we need, let's say, a digital assistant for our community, which is the Earth observation and the Earth science community? So first of all, I think we all agree that, I mean, let's say the human knowledge on Earth observation or science is very much, let's say, fragmented. With papers there, there's technical report on the other side. I mean, and then it's very difficult for the communities, let's say, to cross compare, let's say, information through these different support. As well, that all this this information is sometimes quite technical, either on the Earth observation or the answers part, for which you need to have some technical expertise or thematic expertise. And somehow we want to lower the barrier to, let's say, get those information in a nice way. And I think also for policymakers or decision makers, we need maybe a support for them to really digest this information in a transparent and also scientifically robust way. And obviously here, LLM should be, let's say, the backbone of what we'll be doing, with the idea that you will interact with Earth observation and Earth science knowledge through natural language interactions. There will be as well some way to have some kind of retrieved-augmented approach with so that you will have the LLM, which is kind of the overlying reasoning part, but also you will be able to cite publication references and not only, let's say, hallucinate from the LLM. This is what we want to do. And at the end, we want to move from the paradigm of finding data to also ask questions and get real explanation that are very grounded based on science. Again, here we want to democratize somehow Earth observation, Earth science to any people in the community. It can be the public at large. We want to accelerate the innovation so that any scientific or research access to really type in the vast knowledge that we have in the community and get some synthesis, get a faster literature review on the specific field. We want as well to support policymakers And we want to do that in an open science way, in the sense that everything that we'll be doing will be entirely, say, reproducible with all the source provided and so on and so forth. Just as something which is important here, for now, the first version of this, if this virtual expert or digital assistant is a pure textual-based, let's say, digital assistant, we plan, of course, to enrich these capabilities towards more, let's say, agentic AI, leveraging geospatial tools analysis, also geospatial foundation models, and work if as more like a reasoning layer within an agentic AI system. But that will be for the conclusion, let's say. With that in mind, I like to, no, maybe I can skip that slide. Yeah, now Eve in a nutshell. So I think these are more or less the conclusion of the talk, but I'd like to just give like some few information. So Eve was developed as part of this project led by PySchool together with Imperative Space, Mistral, supported by Wiley, based on Mistral 24B parameters. Everything that we'll be doing and that we'll show will be accessible. So we'll have the web platform, we'll have APIs, and the idea is to provide a new assistant that can answer to any query that you have in natural language. You see some capabilities on the right. I think later on, either Yassine or Alex will detail that. So I guess now I can pass the ball to Yassine, who will deep dive a bit more into why we selected Mistral 24B, what is the current status in terms of LLM, and so on and so forth. Maybe go ahead, Yassine. Thanks.
Thanks, Nicolas. So I'll start very briefly to introduce Mistral. So Mistral AI is like now maybe almost like 3 years. And we have one big motivation, which is like to deliver frontier AI to everyone's hands. So it started as a frontier AI lab, so a research lab. And from day one, we are quite committed into open source. But I would say that the company evolved quite a bit from being simply an AI lab to evolving in all the direction. Like for instance, now we are even in the compute. But the core motivation is still the same. It's still to push frontier AI into the hands of everyone. Yeah, if we can go to the next one. So maybe one thing that is a bit specific about Mistral is like we have a really good expertise in training large models. We have quite a proven training stack and also some high quality data. And this allows us to do a partnership like industry or research partnership. And we ensure that when we do this type of partnership that the data stays in the hand of the partner. And me, I'm particularly in a team, so in the applied science team. In this team, what we do is like we collaborate with some partners or customers, like we did in this case with PySchool and ESA. And we do some research, but we are able to collaborate in many aspects, such as research deployment, and we can help to scale. And I would say something that differs in Mistral compared to others is like we can go beyond simple fine-tuning. We have open models, so we are not restricted into API-only access. So of course, there are other open source model provider like a Chinese provider, Qwen or DeepSeek. But I would say that their offer to research contribution is a bit limited compared to what Mistral can offer. So yeah, I've been told that the audience is a bit generic and maybe a bit Earth observation expert. So I'll just do quick recaps on LLMs and how it works. So AI, what we call AI, I would say it's like we can group that into like all type of systems that can perform complex tasks. So it can go from vision to analytics to recommendations. And inside this one, there is a subset which is like generative AI. And the core of generative AI is like to create or generate content. And this content can be text or images or audio. And this is done by large neural networks. And in this category, there is a subset which is like a large language model, which are focused on text, so specialized on language. So they understand the text and they are also able to generate text. And it's useful to power chat, to do some advanced search, now to do some coding. So it's also the text in all those forms. So it can be raw text, markdown, but also code. So if we now have a look on how an LLM actually works, I'm sure that many of you are using LLM chatbot, but yeah, you have a prompt. So it's simply the input that the user will have. So here the prompt is like, what's the most famous French monument? This prompt will go into this large language model. So that's the inference. You'll make a request and it will try to leverage the vast training data that it has seen to understand the question and formulate an answer. So during this inference, the model will operate within what we call a context window. So it can typically, I would say, it range from 32K to 256,000 tokens. Now some model can even go to 1 million. And a token is like simply like a piece of word. So it's about like 3/4 of a word on average. And we use that because it allows more flexibility and it's a more fine-grained and granular space to represent the language. And finally, the model will do like what we call completion. So it will generate an output. And yeah, if we go on the next one. So actually the way the output works is like it will output token by token. So here it will start with it. Then we have to input again the whole sentence. So what is the most famous French monument? It, and it will output is, and so on up until the Eiffel Tower, and it will continue. So it will continue until there is a specific special token that tells him to stop, or until a certain limit is reached. Sometimes we can allow a specific budget for each generation, so it will go on until this point. And how it works actually is like what's behind this LLM is some model weights. So it's like matrices. It's quite sparse and very big, and that's the ways that we are trying to learn. And what it does, in fact, is like each time it will just generate the most probable token based on what it has been trained on. So now we see that LLM generates text. Let's see briefly how they are built. So first there is the pre-training step. So this step is quite long and compute extensive. It can last for several months. So during this pre-training, we'll see like a massive amount of text data. It can come from internet, from websites, code, books, basically every type of text data. And the model will solve one simple task, which is like each time predicts the next token. So here we have the cat sat on the, and we have to predict math. If the model predicts that accordingly, it will be rewarded and it will be trained and its weight will be updated. So once we have done that, we'll go into the post-training. So the first step will be to instruct the model. So it will be to transform our model that at the moment is only able to predict one next token into something more useful, like a chat assistant. So in order to do that, we need to have instruct data. So we need to have a data that is formatted as we can see here. So we have a user and assistant template, and we'll teach the model to follow this specific behavior. So of course, if we want the model to have another behavior, we can teach another one. And finally, there is a crucial step, which is like alignment. On this step, like we'll teach the model about human preferences and safety. So we don't want the model to answer dangerous questions, or maybe we want to be more aligned with like our values and stuff like that. So it's quite a crucial step. And it's a bit shorter, but there are also many techniques to do so. After that, typically the model is released. And of course, we can customize this model even after this step. This is what we did in this collaboration with B-School and ESA. And there's many type of customization. It depends on many aspects, like first, how many tokens do we have? What type of customization do we have? If we want to inject knowledge, or if we want to change the behavior, it's different type of tuning that we'll use. There is one thing that is important to have in mind is, like, I would say, the trade-off between performance and cost of a model. So the larger the model is, typically the better it will be, but also the more memory and the slowest to answer it will be. So there is some type of most attractive quadrant, so in orange, and that's the area where we want to be. So those results are quite old, but you get the idea. And typically we try to select models that are in this quarter, and we try to have models that are in this quarter. Yeah. So actually at Mistral we have many models, many type of models, some generalist models, some specialist models. So on the frontier generalist model, like now we have, for instance, Mistral Lab 3 that was released in December, and those type of models are now like multimodal. They are able to process images. At Mistral, the models are also multilingual, so we support 12 plus languages. The code models are able to use more than 80 languages. Some of the versions are reasoning models, so we try to push for more advanced reasoning capabilities. And yeah, we have like some specific models. I can think of the OCR models. It's a VLM specifically designed to numerize scans. But you also have like more experimental models, like small creative, or models that are dedicated to coding, like Devstral. Yeah, so actually us, when we started the project, like the model in this quadrant were the one that were interesting for us, because we wanted to have something that we could deploy after that, because the goal was to build a system that could be used and at manageable operational cost. But when we began, actually, the Mistral 3 models were not available. So it was quite natural to start from small 3. We had a version of the 8B and the 3B, but they were quite old compared to Mistral 3 that just had a release. And also Mistral 3 had quite a good reputation on being an easy model to fine-tune and to adapt. So we started from this point. But of course, now maybe the 14B could also be a decent alternative. Yeah, so LLM, they are quite powerful. They are now maybe a bit everywhere, but of course they have some limitations. First, an LLM will not know about proprietary data or domain-specific data, because like it's typically trained on public web data. So there's a certain limit that on knowledge that one model can have. Then I would say that the LLM do not have real-time up-to-date information. For instance, Small 3, the cutoff was like end of 2023, which is quite old. So it's quite important to have like more updated data if we want to have a relevant system. And one aspect which is quite critical is like LM can hallucinate, because like sometimes they can confidently generate completely false information. It's quite malicious and quite dangerous. So to address those limitations, there are ways, like one of the approach is to rely on RAG, so retrieval-augmented generation. This involves providing the LLM an external, up-to-date, proprietary or open data sources, and we do that at the time of inference. So when the model will answer, we'll retrieve some information before generating, before doing the completion. Like that, we'll ground the answer in facts. Another way is also to connect with tools. We can think of like providing internet search or more agentic capabilities. So the more tools, the better. And for this project with for Eve, we decided to go for the RAG, and Alex will surely show you how it was implemented.
Thanks, Yasin. So yeah, let me start. Maybe we can move on to the next slide, I think, Nicola. So let me start by giving you a bit of a high-level overview of the entire project, essentially. So both from the development of the system to the actual usage. So initially, we started, as Yasin was saying, with an open-weight LLM, specifically Mistral Small 3.2. And then from this, we got two streams of data, essentially. The first one is large scraping that we do on Earth observation and Earth science domain data. These are mainly peer-reviewed articles, but also documents from certain reputable websites, etc. And we also add to it some general domain data, mainly in the form of replay data. So this is data the model has already seen, and we essentially add together with the new data so that it will not forget its general capabilities, essentially. So based on this Earth observation domain data that we got, we do synthetic generation of instruction fine-tuning data. So this is essentially turning the raw data that could be an article, for example, into, for example, pairs of question-answer or things like this. Then we do what we call instruction fine-tuning, which is a form of supervised fine-tuning on the model. We get into an instructed LLM that will be already more specialized into the domain. And then we align it with some preference data. So preference data is going to be data that will have usually two pairs, a pair that is preferred versus another one that is not. And the result of this is an aligned model. That is what the user will actually see. At that point, then, with the actual system itself that we have, the user query then is given to the aligned LLM itself. Then the model is connected to a variety of external tools. Mainly now they are RAG databases. So these are knowledge bases of documents, of curated peer-reviewed documents. But other tools can also be connected, like a code IDE or a calculator, or even possibility of creating a computer vision model, etc. And then the output of these tools is integrated into the model itself to give the actual final answer to the user that they will actually see. So this is a bit of an overview as well of most of the data that we've used. So initially, we have the raw data that we scrape. So this is, as I say, mainly scientific EO and earth science data. So from this, we get around 5.7 billion tokens of open access data from various sources, mainly journals. And through a direct licensing deal with Wiley, we also get around 1.1 billion tokens of closed access data. In addition, we create manually from scratch around 5,000 samples that we mainly use for evaluation. These are instruction data sets. And then from the initial raw data, we generate synthetic supervised fine-tuning data, more than 100 million samples. Together with the authentic SFT data, we also have manual preference data, likewise, for evaluation. And then we perform a curation and a selection of the original raw corpus, and we have the subset of documents that we put into the RAG database itself. And then finally, we also create manually an hallucination test set to evaluate detection, essentially, of the model into hallucinated text. So the sources of the scraping are like this. So on the green, you can see the open access, and on the dark blue, you can see the closed access. So we have the widely closed access summing up to around 1.1 billion tokens. And then everything else is open access. So MDPI, Copernicus, and CBI, subset of open access of Wiley, etc. If you put everything together, then we have around 5.3 billion tokens, more or less, that we can work with. And from this raw data, to actually create the corpus, we do the following. First, we identify manually the trusted sources. So this, we operated not at the document level, because that would be unfeasible, of course, but at the journal or publisher or website level. Then we perform some web scraping. And then once we got this raw data, we perform a text and structured text extraction into Markdown. So we actually have sections, subsections, tables, etc. Then this is cleaned and deduplicated. We also remove personally identifiable information. We also perform filtering of domain-relevant content from large-scale datasets, dumps that you can already find. And then we enrich all these documents with relevant metadata, such as journal, years, amount of citations, if it's a paper, etc. And the actual resulting clean corpus, the subset of it that, license-wise we can open source, and the code base to do this, we will open source to the community. In addition, we also create, as I said before, authentic instruction data. So for this, we have around 30 annotators, mainly academic from the EO Earth Science domain. We create around 6,000, give or take, samples of Earth observation datasets in various combinations of question answering or factuality or preference in the form of A/B testing. And this data, which will be released, can be used to ground generation of additional synthetic data, or like we do in our case, for evaluating the model itself in data that for sure has never seen, because of course didn't exist until now. So on the compliance element, as I said, when we have the process data, we remove any kind of personally identifiable information. So that is names, emails, phone numbers, and things like this. And we only release the anonymized corpus. Then we only use, of course, permissive or legally secured sources. And for all the data that we will open source, we perform extensive tracking and registry. And together with the corpus, we provide an attribution file with all the metadata and relevant license for each document. Now, once we have this already cleaned, anonymized, ready-to-go corpus, then we generate synthetic instruction data. So the model, of course, until now cannot just be trained to simply predict the next token on this data, because it wouldn't be trained to perform to follow any actual instruction itself. So at a high level, the idea is to create structured data from this unstructured corpus. And the idea is to have something like this, with this structure of some kind of context, some kind of query, and then some kind of answer that the model should be actually trained to predict. That is the part that we train the model to do itself. So the important thing is to ground the model that is generating this query answer pair with some kind of authentic context to minimize hallucinations. Technically, we could remove completely the context, but it would make it easier for the model to disperse, let's say. So we define a pool of models that we use for generating and evaluating to maximize diversity. Some DeepSeek versions, GPT, Mistral, etc. And we generate these various combinations of question answering on the original data with various pairs. And to this, as we said before, we also add the data replay that mainly comes from Mistral data, as I say, to minimize the chance of any kind of catastrophic forgetting on the already existing capabilities of the model before the fine-tuning. So the general idea works like this. So essentially, we have a corpus, and then we have a pipeline pool, let's say. So pipeline pool, what I mean by this is the different kinds of variations of the structured data that we want. So I will go a bit more in depth now. Yes, so based on this corpus and the different specifications of each pipeline, we have a generator pool of models that we sample through. We generate the samples, which are, as I say, some combination of query answer, essentially. And then we also have the evaluator pool that will evaluate the quality, essentially, on a variety of criteria. And we filter the samples that are not relevant. And the remaining filtered subset, that is the actual data set that we use. So these pipelines are several. So first, we have document base. So that means that we just generate some QA pairs directly from full documents. So research papers and things like that, as I said. So pretty large context for the most part. We also generate questions that cannot be answered with the provided context, with the aim of training the model to discern when the query cannot be answered appropriately based on the relevant context that it has. Then we also do some multi-document generation, so not from just one single document of context, but from several documents. The idea here is that at inference, the model will have a connection to this RAG database and therefore will query different documents. So we want to train the model also to be able to reason across different chunks from different documents. This includes both long context and hop weaver, which is a technique used to make the model reason across different chunks, essentially on context. And then some identity data, essentially to give basic model information to the model, like who created you, who developed you, things like this. All of this is always evaluated, as I said on the diagram before, with an LLM as a judge. So this pool of LLMs that is offering a critique, essentially a justification on the sample and deciding whether to keep or filter. And then with just the raw pre-trained data, we use a technique called active reading, which essentially means that the model dynamically chooses different learning strategies on how to learn from this raw data unstructured based on both task-specific and task-agnostic data itself. So the data mix, therefore, is something like this. So as I said, we have this 5.3 billion token final corpus once we do the processing, of which we generate around 22 billion tokens. Then we perform filtering, of which we are left with around 10 billion tokens with the different pipelines that I described before, active reading, hop weaver, etc. These are all the different forms of the structure of the IFT. And then to that, we add 17 billion of Mistral data, of which 15 is replay data and 2 billion come from Mistral space. The final training mix, therefore, is 35% pre-training and 65% fine-tuning. Oh, yeah, it's okay. So the process of fine-tuning is as follows. First, we define the goals, the use cases of the model that we want to actually use for, which means we choose the task to specialize to fine-tune on. That leads us to define the baseline and the evaluation metrics that are more suitable to the task. And then we work on building the task-specific data sets, picking a base model, and setting the hyperparameters for the fine-tuning job. We run the job, we evaluate, and then we iterate over this loop until we get the highest scores, essentially, that we can on the development scores. So regarding the experiments specifically, we use low-rank adaptation. So this is a parameter-efficient fine-tuning technique. That means that we are not fine-tuning all of the weights of the model at the same time, but instead we are adding these small matrices of initialized weights that we train only, and then we combine them, we merge them into the main weights of the model. We do also full fine-tuning. We compare also with full fine-tuning with replay data as well. And then we do short loops of SFT by generating and scaling fine-tuning data and assessing the impact that each technique has and adjusting the balance, the percentage of the replay of the pre-training data from 10 to 80%. So the final chosen model, therefore, is the combination of all the models that we've obtained in these different experiments by doing model merging, weight averaging. And this is a bit of a peek regarding the compute. So this is not just for the fine-tuning, although most of it comes from the fine-tuning. So first, we have three big sources of compute. The first one is Mistral compute, where we actually fine-tune the model itself. Then we also used Mare Nostrum primarily to do synthetic data generation. And then for a variety of tasks, we also use some other private cloud compute like Roundbot or Lambda Labs. So the three main usages are synthetic data generation and evaluation, the actual fine-tuning itself, and then miscellaneous tasks like data processing and so on, which percentage-wise, they are very minimal in terms of requirements compared to the other two. So you can see the table a little bit what we use. So in terms of you have GPU hours, and then you have a rough estimate of the equivalent in in CO2 based on standard ratios, more or less, on the community. So on the synthetic data generation itself, we spend around 54,000 GPU hours, and on the fine-tuning and evaluation around 175,000 hours. So putting everything together in CO2 equivalent, you can think of it in terms of the annual energy of around 25 average homes, or driving some normal gasoline-powered passenger vehicle for around 150K kilometers, more or less. So with this, we have the actual fine-tuned checkpoint itself, and that is something that, of course, you can already use, and the output of that will already release, so people can use it by itself with doing other fine-tunings or deploying them to their own applications, or etc. Right? Then, in addition to the checkpoint itself, we work on a RAG workflow to connect this checkpoint to the curated knowledge base that we were mentioning before. So the basic idea of RAG, without getting too much in detail, essentially, if you look in the top right, we're going to have a user that will give a query. Then here we are not saying it, but actually we do a requerying. So we use an LLM to modify the query, so maximize the retrieval of relevant documents. That query then is embedded into a vector space, and then we separately, into that vector space, we populate it by making chunks of the original data. So this original data is cleaned, chunked, and embedded, and put in the vector space. And then what we do is essentially we just measure the similarity between these different embeddings of the chunks that we have in the vector space and the current embedding of the user query. We retrieve several documents, we do re-ranking actually, and then we integrate it into the prompt template and the query, and we give it back to the model. So it has the query as well as all this additional context, and then provides the actual answer to the model. Then in addition, we can do a loop that I will go in a bit more detail now regarding the model re-fact checking its own answer with respect to the vector database. So onto the database itself, it looks like this. So we have the bulk of it being populated by open access documents. So these are a curated list of the documents that we retrieve based on whether they are peer reviewed, based on the year of publication, etc. That's around 270K documents. Then we also have, through the same licensing deal that we mentioned with Wiley, around 67,000 documents that are closed access. Then we have around 10,000 documents specifically on a variety of ESA sources, websites, and things like that. In addition, a user can create their own private collection and upload their own documents, whichever one those might be. And then finally, we have essentially as a kind of fallback, 24 manually picked sources that the model can also verify. So these are going to be things like, the EO portal and, Copernicus data and things like that. So to embed, we use Qwen34b after some experimentation, and Qwen34b also re-ranker for the re-ranking itself at 124 batch size. So the original documents are chunked using a combination of hierarchical chunking and length-based splits. So the nice thing about this is that each chunk more or less is reasonable as a standalone. It should be mainly sections or subsections of the original document. And then these chunks, as I said, we enrich with metadata. We extract first the DOI by using some OCR extraction, and then with that DOI, we query archives like Crossref to extract larger amounts of metadata, like the URL of the original source, title, journal, etc., which we all provide at Inference. So in addition to this, we also have a detection loop, essential detection loop that the user can query at will. Essentially, the idea here is if we start on the top left from if, so if will give an output, and then if we want, we can query the loop, so it will begin a span detection or a flagging detection loop, so the model itself will reevaluate the answer prompted slightly different as an evaluator evaluate the answer, whether it's suspicious, essentially, of having some kind of factuality error. If yes, it will try to reprompt this answer by focusing specifically on the parts that are more suspicious. And with these new queries, it will try to do another retrieval on the database with the expectation that we will hopefully retrieve new documents that we didn't retrieve the first time. At that point, then, we give again these documents back, back into the model, and we compare essentially the two different answers of the two models, and we rank them. And regarding the evaluation, we do evaluation on two different kinds of benchmarks. So the first ones are general domain benchmarks that are already existing. So MMLU is a multiple question answering standard benchmark. GPQA is QA on university level questions and so on. We do both zero and few shot evaluation. So that means if the model is shown any kind of examples of the kind of answer, of the kind of samples that it will see or not, and also some selected high quality and structured text. Then on the EO Earth Sciences one, all of these are the manually created document datasets that we do. So we first have an open-ended QA without context. We also have an open-ended QA with context. So these are, as I say, mostly papers and so on. We also have multiple choice QA with only a single correct answer, also one with several correct answers. We have an hallucination detection dataset, a refusal dataset, and right now we're working on a humanly annotated A/B testing dataset as well. So for all these datasets, we use the standard metrics like LLM as a judge for the open-ended kind of tasks, manual preferential ranking, F1 score, accuracy, etc. And as I say, all the EO datasets are manually created and will be open sourced. And this is a sneak peek of the evaluation, not yet fully complete. There are still some tasks that are missing. So in the dark blue, you can see the actual checkpoint itself. And on the dark green, you can see the baseline model. So the first benchmark is hallucination detection. So these are relatively hard to spot samples that contain some kind of factuality error. You can see that we are above the baseline. We also have a couple of multiple answer and single answer multiple choice QA. Then we have the subset of astronomy of MMLU. So MMLU itself is not something that we created, it already existed, but we take the subset of it as an evaluation as well. We are above the baseline null. And then we also evaluate on the general benchmarks to gauge how much drop or gain on the general capabilities the model is having. So in addition to MMLU astronomy, we also do the entirety of MMLU, which will contain all sorts of domains from history to literature to sports, etc. And GPQA Diamond, which is, as I said, university level kind of QA dataset.
If I can just comment quickly on this one. Yeah, we also got good results on every open-ended evaluation, which is nice. So basically, we are above in the evaluation we created. And one thing that we also focused on tracking was like all the tool calling evaluation, because in fact, we did not want to just have a model that knows stuff. The goal was to have a model that is able to use the RAG database and that is able to be a chatbot. So that added some complexity. So internally, we tracked all the tool call and tool use evaluation, and we noticed some nice gains in those ones. We'll try to maybe highlight that in the contribution. And one thing that is maybe missing here also is like we also compared that to other models. And the Mistral Small 3.2 was quite a high baseline compared to other models. So it was quite reassuring to see that. And of course, in generic evaluation, we noticed some losses like in GPQA, but also some nice gains. We noticed quite nice gains in mathematical evaluations and even some coding evaluations. And we'll report that, of course, in the technical report that we share with the team.
Thanks. Yes, with this we can finish a bit with a general overview on the limitations and the conclusions of the work so far. So indeed, we started with, as Yassine said, with a high baseline score already compared with other models within the same size range. Another issue is that probably we are fine-tuning primarily on open source data, which means that the baseline model has likely already seen that during the pre-training. And right now we are finishing, as I say, some human preference on A/B testing with other models and the system-wide evaluation. So meaning also evaluating the entirety of the assembly of the requerying and the retrieval-augmented generation knowledge bases and so on. And I think that's all for me. If I don't, yeah. So now I give the floor again, Nicola.
Yeah, thanks a lot, Alex and Yassine. So let's deep dive a bit more into the system. So the system will be like any chat system in the sense that in the middle you will have the main aspect. You can discover what Eve is about, giving some few tips on what Eve can do, what Eve cannot do as well. Yet, as I said, for now it's only entirely based on textual informations. You can have access to your login profiles, and you can fill names and everything. You can also check, as it was mentioned, well, about CO2 equivalent. I guess it's very important for the user to know exactly what is his usage of the tool and how it impacts in terms of CO2 equivalent. So you can automatically compute based on your various prompts what is the equivalent CO2 that you emitted somehow. And of course, you can check different things. And one aspect that is important is also to all the aspect linked to privacy policy. And this is something that you can also access via the graphical user interface here. That being said, you can look at various options in the prompt or the way you interact with the LLM. You can set up a parameter which is called the temperature, and the temperature is like acting like a proxy for the creativity of the model. So if you put a 0, the model will be super deterministic. If you put 1, it will be super creative, let's say. The RAG as well could be configured with a similarity threshold that can be set in between 0 and 1, filtering more or less the way chunks are retrieved. You can set up the maximum document that you want to get, the years, the journal, and also you can define what is the minimum citation that you accept from the RAG to retrieve. And if you want to accept only very well-known publication, then you set to very high value this criteria. Once you have saved that, you can look at the various collection of data that we have, and I think it was presented by Alex before. As we mentioned before, we have access as well to Wiley documentations. With in mind as well Wikipedia subservation document. We have our own open source Eve documentations, and we have as well another collection which is all ESA documentation that you can also tap in via the system. And as you can see, you can enable and disable as you wish the different collections. You can also create your own collections and input into the system your documentation that you want to interact with. And yeah, just give an example. I create a collection, and then you can browse the different files into your local repository and then input any documentation that you want and for which you want to interact with. Once you have done that, you can, of course, look at the different, let's say, interaction. Well, no, it's not the right one. Yeah, you go. You can, of course, have a new chat and also look at the previous chat that you had with the system before. So you can always look at your history. And yeah, just give you one or two examples, with the first one being, okay, tell me, okay, which new space actor can be good at providing information about metans? And yeah, it can, as you can see, it can list you and provide like nice table of what could be the different Contributors in the community. On the right, you can see all the sources that was retrieved from the system. You can link and click on the different publication and access directly to the web page here provided by Wiley. You can as well prompt your own question, obviously. And for example, an example where you ask, explain in 10 bullet points how deforestation impact climate change. And here you see the lively response from the system. And as we are all used with ChatGPT here, you have the same. I mean, it lists back all the different 10 points that you wanted. And again, the nice thing is really the possibility to look at the different sources. Here we set in the system only 10 sources to retrieve. So if you click on source, then you will see again the list of documentation which are extracted. You can also click on show more and then look at the specific chunk that was actually retrieved from the system. Last point, which is about hallucination detection, and here I'll just showcase an example whereby I asked to the system what is a CubeSat with different proposition. Okay, a CubeSat is a miniaturized satellite based on 20 centimeter cubes or 10 centimeter cubes, and here you have actually 4 different answers. And then you will see that we'll activate these hallucination detectors because the first answer provided by the system was somehow not so correct. It says that it just gave you the answer, okay, it's a class of smaller satellite based on the 10 centimeter cubes, which is, of course, not entirely correct. So if you click on hallucination detection, then here you have a bit more rational explanation on this question, and you have some kind of nuances into the reply. So here you see more or less all the features from this first version of the EFA system. Of course, well, as you may know, we had a pilot phase demonstration that occurred last fall from October to December, whereby we collected many, let's say, input and feedback from the community. So we accepted about maybe 200-300 or maybe a bit more beta users. And again, from that experimentation, that pilot phase, we got many feedbacks, and the idea now is to improve the system based on those feedbacks. As it was mentioned before, everything that will be that we are doing here will be open source. So the model, the dataset, the benchmark that was described by Alex, but also all the backend system, all the overall system will be open sourcely available to the community. And I hope it will come very shortly. I think it's a matter of maybe a few weeks before we release the whole package, let's say. And we plan to, let's say, continue the operation of the ETH system, and that will happen probably in Q2 this year. Last but not least, indeed, we have many perspectives to this works. For as of now, the system is entirely based on, well, textual information. We want to move really towards more like an agentic AI with this Eve acting like a reasoning layer and activating different tools. It could be about geospatial analytics. It could be about VLMs or visual language models, foundation models. It could be also database, corpus documentation, so on and so forth. So please stay tuned on that, and I think this is it for this webinar. If you have any question, of course, maybe we can take a few questions now. It's just 3 p.m. If not, of course, please feel free to reach us by email. Maybe this is something that we can put in the chat. Over to you, Christian.
Okay, thank you to everybody. I've seen Alex, Nicholas, was great. I would say yes, let's try at least 2 minutes more if there are any questions. I don't think it's a problem. Feel free to raise your hand, unmute yourself, or write your question in the chat. We're going to read it, and we will be happy to answer.
I just have a small question. So can we have like early access as a researcher when we can be part of the testing, like the pilot phase, and test us from our end?
I think if I understand correctly your question, you want to get access as a beta user as well, the system. I think it is still possible somehow, even though we officially, let's say, closed the pilot phase, let's say, last December. If you gave us your credential, I mean, basically your email, then we can register you in the system and you can have access for a specific number of days, let's say, just to try the system. This is something that we can do.
Okay. Thank you.
I see the chat system is off. If you like to get back to us by email, I mean, my email is nicolas.longepe. I should have written here my email, nicolas.longepe@isa.ent. But I guess you can easily find our contact as well online. Peter.
I just had a small question. So I really liked the hallucination detector in the example you showed at the end. And did you try this with another chatbot and just see if he completely hallucinated on the EO questions?
We benchmarked several models on the detection element itself. We fared quite well compared with the very, very, very large models. There's still a bit of a gap, but within the size range, on the detection element, we fared pretty nicely.
Okay, and there was an advantage of F with EO-related conversations compared to others?
Compared with general domain, you mean hallucination evaluation?
Yes. Yeah. Sorry.
We didn't test because we created the data set specifically on EO-related hallucinations.
Okay. Thank you.
Any other questions?
Yeah, I see a question about catastrophic forgetting. Maybe I can.
Yeah, on the chat.
Answer this one. So the question is like, was data replay the main strategy to reduce catastrophic forgetting during the training stage, or was additional strategy used? So yeah, it was one of the main strategy actually used, and I would say like we were quite in the middle of many positions when we decided for which strategy to pursue, because we had too much token for LoRa to be efficient, but at the same time we didn't have enough token to go for continuous pre-training. I think it would have been easier to learn facts with continuous pre-training because this is the easiest way, but the number of tokens was too little. It would have implied to add too much Mistral token, so maybe it would have not been enough space. So we decided to go for SFT. But if you check, like the ratio between SFT and pre-train is not standard. Like 35% is quite a high ratio of pre-training because we try to add as much as possible pre-training data and active reading data that we generated, which is like some type of pre-trained data, so not instruct. But yeah, I would say like merging also allows to prevent a bit overfitting because we are able to select some checkpoints that were really good in generic capabilities that we obtain versus some of them that were quite bad. Like if we have a really high ratio of Earth observation data, we were able to really benchmark the Earth observation benchmark, but the model was a bit fried and was not super useful to be used as tools. So it was a bit a compromise.
And regarding the question from Mike, right now the system for the pilot users is hosted in data centers in the ESA state members only using RunPod right now as a pilot solution essentially.
And maybe if I can just add quickly on this catastrophic, like one thing that we struggled a bit was like to learn the difficult facts. And this is why you can see we iterated a lot with P-School to filter, to judge, and to regenerate new synthetic data. And we throw away a lot of synthetic data that we actually generated because it was too easy or not super useful. And since the model, as Alex said, was already trained on many public access data, we needed to identify the difficult data that the model did not know. And also, like, to be able to learn those facts during SFT, we needed to have a scheduling that was a bit higher in terms of learning rate than classic scheduling. And therefore, we needed like a strong replay, like this was like critical. And LoRa was not super useful on what we observed, but it added some diversity, at least in the merging. So, and it was also a nice baseline.
We have a question from William.
Hi, thank you. Is there any possibility of getting API or some other kind of programmatic access to E?
Yes, that will be provided as well. So it will come with the GUI, but also the APIs, of course. I mean, of course, yeah. That will be the case. Okay, do we have any question? Because I can't see the chat. I don't know why. It's turned off for me, so I can't see if we have any other question. Cristiano?
I can see the chat. I see people that wrote. So basically, we answer all the questions, and they are just thanking us. So thank you so much to everybody.
Okay.
I would say, tell me, maybe we can still have one question if you raise your hand or write it very, very fast. Otherwise, we can quit the talk here. Okay, it seems no other question. So thank you again. I remind you for next Phi-talk. The next one will be exactly next Wednesday. So check on the web page. I just link in the chat. So I would say thank you again to Nicolas, Yassine, and Alex. It was super interesting, and this is a huge project that PySchool, Mistral, and ESA Fh-lab are doing together, and it's super interesting. So thank you again to everybody, and see you next week.
Thank you for attending. Bye bye. Ciao. Cheers.
Bye.
Thanks, everyone. Ciao, ciao.
Ciao.